Now I'd like to talk about why it is that the low light level performance of cameras is often so poor. And the fundamental problem here is actually quantum mechanics, in particular photons. If we imagine our detector, it's got its pixels, and what we're trying to do is measure the intensity of light that falls on each pixel. So there might be 17 watts per second here and 15.3 watts per second there or whatever, and that map of intensities gives us an image of smiley face or whatever it might be. The trouble is that light can't have any intensity because it's made up of particles, of photons, quanta of light. So you can have 2 photons in a particular pixel or 3 photons, but you can't have 2.5463 photons. Photons come in lumps, integers, and that introduces an unavoidable level of noise, dividing things up into distinct levels rather than perfect, smooth values. But it's worse than that, because the arrival of photons is a random process. Let's imagine we have a 0.5% chance of a photon arriving per second. That means that on average, every 2 seconds you get a photon. But does that mean things are perfectly regular? 1, 2, photon, 1, 2, photon, 1, 2, photon. No, it doesn't. On average, it might be every 2 seconds you get a photon, but you might sometimes get 3 in a row and then nothing for 10 seconds. It's like flipping coins. Every time you flip a coin, there's a 50% chance of you getting heads. Does that mean you alternate heads and tails? No. You can get a whole bunch of heads in a row and then a whole bunch of tails or some other sort of pattern. So this, it turns out, is the fundamental problem. And to work out how bad it is, we're going to have to work out how many photons are arriving at our camera in a given amount of time. Now, quantum mechanics tells us that the energy of a photon is given by the equation E, energy, equals h nu, where h is Planck's constant, which is 6.63 by 10 to the minus 34 meters squared kilogram per second. And nu, the Greek letter nu, is the frequency in cycles per second. So what's the frequency of visible light, the sort of light we want for a camera? Well, for this we're going to need another equation. We know the wavelength of light. Visible light's about half a micron. What does this correspond to in frequency? Well, for any wave, not just light waves, just imagine you're watching a wave go past. You've got a wavelength, normally written with the letter lambda, from peak to peak, and that's going at some velocity, in this case c, and it's got a frequency, which is the number of peaks that go past per second. So let's imagine you're standing here, watching the wave go past. You count the number of peaks that goes past per second, 1, 2, 3, and you know the wavelength of each. And the speed is just going to be the wavelength times the number of peaks. So if the wavelength is a meter and 3 peaks go past a second, then the wave must be going at 3 meters per second. What that's telling us is the speed equals the wavelength times the frequency. And that's a generic rule for any wave. What this means is that the frequency is just equal to the speed of light divided by the wavelength. So in this case, that's 3 by 10 to the 8 meters per second, all over about 0.55 by 10 to the minus 7 meters, which comes out as about 5.5 by 10 to the 14 hertz. Very high indeed. So this is just a ridiculously high frequency. So if we multiply that by Planck's constant, using this equation up here, we find that the energy of a visible light photon is about 3.6 by 10 to the minus 19 joules. So you're not going to power your house for a month with 1 photon of visible light.